Okay, so welcome. On the last lecture, we started to discuss groups, actually Lie groups, but we don't know yet what is a Lie group, and we need the concept of manifold for the definition of Lie group. So we just learn about some particular groups, and we will see next that they will be Lie groups. So what was the basic idea? That you have to have some set and some structure on it, such a pair, structured set, and then automorphisms of this structure set. That means bijections S to S such that this exists are now interesting for us because such bijections can be composed and these elements, when as elements of groups are taken these bijections and the composition is like multiplication in the group, you can check that everything works. So by this procedure, one can define a group. But the really interesting group comes from the structure on the set. There are plenty of structures, and depending on what structure you choose, you obtain corresponding group. So we discovered in this way group GLV, which were bijections of linear space, including this linear structure. And when one chooses a basis, it can be transformed to the group of invertible matrices. This is the group of invertible abstract mappings from V to V. And if you choose a matrix, you have a formula that A on EA, or by definition, this guy is B, E, B. This is from here, and this is from here. Yes. So A is an abstract mapping, and these are elements of matrices from GL and R by this definition. And if you compute what happens with compositions, you will see that it is A, B, B, or C, C, D, which is exactly matrix multiplication of the corresponding matrices. So we see that it is an isomorphism of these two groups, yes, by this formula. Then we studied further structure as more rich S, and we added to this V a bilinear form. Now, the preserving of bilinear form is defined in this way, that whenever you have two vectors and compute the value of the bilinear forms of them, you will need that AV and AW has the same value of bilinear form. This is the definition. One can compute it in components using basis and come to another interesting group, which is called ON, orthogonal. Matrices are given by this equation. So this group, and also we discussed a little bit, not in complete detail, because to discuss it in complete detail, we need something which is called forms, and it is only explained in chapter 5. Now we are in chapter 10, by the way, but without 5. So in chapter 5, one starts to learn what is a form, further differential form, but in chapter 5 it is just linear algebra. And then we can learn that if we have parallel epipeds, here is with just 3 vectors, and construct, well, this parallel epiped is something like this, but generalized to n dimension. This has some volume. And if you apply linear mapping on all 3 these vectors, you obtain a new parallelepiped with a new volume. And the new volume is some multiple of the old volume, some lambda. And this lambda turns out to be determinant of the matrix. So we can define special matrices once again, not orthogonal, but matrices which preserve volume. And after computing, for which the best thing are these forms from chapter 5, we obtain that, well, if for computing that this is true, yes, if we already know that this is true, it is clear that the group is given by this equation. And this group is called SL and R, special linear. Yes, so this is the most general matrix group. This is one possibility to make it somehow special. This is another possibility to make it special. And here we can also define groups OPQ, more general than this ON. I mentioned it in the last lecture, that if our bilinear form has P pluses and Q minuses, not just all pluses, then this group comes out to be this one, which is more complicated. This is interesting group also for physicists, because in special relativity we need it for 1,3 or 3,1. It depends on convention. And then there are combinations. For example, this combined with this, that orthogonal matrices with determinant 1. By the way, this is not very big restriction, because orthogonal matrices can have determinant only plus or minus 1. So if we choose this plus 1, we just put away this minus possibility, not too much possibilities, just 1. But it is interesting, important. So SON or SOPQ is also very important group of orthogonal matrices which preserve volumes. So with determinant of matrix 1. And now I just want to add some complex matrices. First of all, we have GL and C, n by n complex matrices with a non-zero determinant. Otherwise, it is not a group. And there are also very interesting groups, UN and SUN. UN is given by A plus A equals to 1, and SUN is A plus A equals to 1 plus determinant of A equals to number 1. Now there is a question, natural, that what structure is behind, for example, UN? Actually, behind any group, there is some structure which the group preserves. So among, for example, this group, the structure is very similar, like this structure behind orthogonal groups. They are called unitary. U is from unitary. And I think that at least in linear algebra 2, something was said about unitarity and so on. So what can we define there? we can define something like this, but this is warning, it is not our bracket. It is bracket from linear algebra, which is called Hermitian scalar product. Hermitian scalar. It differs from the usual scalar product that it is produced out of complex vectors or vectors from complex linear spaces. And if you multiply a vector on the right-hand side and left-hand side, different thing happens. That from one side, the number goes out like usually, like in a real space, but from other side, it jumps out complex conjugated. It is, by the way, much more interesting in complex vector spaces than the normal scalar product, so-called normal. So this is normal for complex vector spaces. From which side there comes out this complex conjugated, it is a convention. And what is funny that convention in mathematics is completely opposite to the convention in physics. You can see it because in physics, this kind of scalar product is used in quantum theory. That quantum theory mathematically uses very much this Hermitian scalar product. And there is some definition, of course. It is called Hilbert space, especially if it is infinite dimensional. So sometimes you can read also the name that Hilbert space also for finite dimensional cases. I think that officially it is only for infinite dimensional. It depends on the definition. So if you know something about Hilbert spaces, there is some definition that this number jumps out differently from here and here. And if you have a look to physics books and mathematics books, it is just opposite. So have a look which book you are just study and how it is defined, because some details then depend on it, on this choice. So you can check that if we define this, for example, as V complex conjugated 1 W1 plus V complex conjugated N Wn, that means that this complex conjugation is from here now of the scalar. You see that these numbers are complex conjugated. This bar means complex conjugation here. So if you do something like here, that find matrices, matrix A, which when applied to all columns, so both V and W, this is the application on V and similar on W. And if you now want that this is our action of matrices on columns, and let's compute this Hermitian scalar product before application of this A and after, and let's assume that it gives the same. So you will obtain a restriction of this matrix, which is very similar to the restriction to On, but there is some complex conjugation. You either know it from the linear algebra, or you can have a look to chapter 10 of my book, where it is in all details. I just want to say that it is also an interesting structure behind this group. And SUN is the same like there, that it is addition of determinant equal to 1, which, by the way, now is more restrictive, because the determinant of UN, you can check from this definition, that determinant of A is some e to I alpha, some complex number of modulus 1 on unit circle in the complex plane. So if you restrict it to 1, it is quite big restriction. In general, it is somewhere here on the circle, and you say that the determinant is here. In ON case, we have just here and here the possibility, so you just throw away this possibility, but for UN, you throw away a lot of possibilities. So there are groups which you have to know about quite a lot, and we will do something with them, and we will learn some information. But of course, you have to know always the definitions. That when I speak that ON, you must know that ON is this and these groups, this and this group, which, by the way, which is here defined here, UN here, and so on. And we will also speak some 2 weeks in 2 weeks about Lie algebras. It is also still linear algebra. One object from linear algebra is called Lie algebra, and it is intimately connected with those groups, with Lie groups. These are Lie groups, and it is very, very important if this group is expressed as matrix group. There are also Lie groups which are not directly matrix groups. We will see one simple example which has the nice property that although it is not matrix groups, it can be somehow transformed to a matrix groups very easily. But you can also have somewhere Lie groups which are not directly given by matrices. If it is in general, you can treat Lie groups by methods of differential geometry. If they are not metrics, it is more or less the only way. If they are metrics, Lie groups, there is some simplified way how to treat them, or many things to do with them without differential geometry. And actually this course, Mathematical Physics number 1, only treats Lie groups which are matrix Lie groups, and this simplification which brings this metricity of these groups. Yes, that how to do with general Lie groups, we only study in chapter 11 of the book, because up to chapter 11 we are already prepared from the point of view of differential geometry to do the work which is needed. But now we are not, but we are already prepared because we know how to work with matrices, and it turns out that some simple machinery with matrices can do a lot of work instead of differential geometry, and it is simpler. Yes. So because of that, we like very much if groups are matrix groups. Matrix groups is some subgroup of this group. This is the biggest matrix group for some n, and for example, ON is also matrix group because its elements are matrices, so elements from here, but some special matrices. But any special matrices, if they form a group, it is called a matrix group. Now, there is an important group which directly is not a matrix group, and it is affine group. Or group of affine transformations. I will do it only in terms of matrices and columns, because the theory of affine spaces is a little bit more complicated, this abstract one. It is like with abstract general linear spaces, but in affine it is still a little bit more complicated. But the work with matrices and columns is very simple. So we study with some x from Rn, so column, and we do a transformation of this type. So in detail, xi goes to aij xj plus small ai. So we see that the transformation is given by a pair, where this is in general from GL and R, and this is from Rn like X. So these A and X are objects both objects from Rn columns of real numbers. There is also a complex version of this, but we do not need it now. So the new thing is this guy, yes, that we not only multiply columns by matrices, but we add some additional column to this multiplication. This part is called the linear part of this transformation, and this is some addition of some constant vector from Rn, and altogether this works as translation. If you think it over, what do you do? For example, you can take the simplest case with A is that nothing with a capital A, so put here unit matrix. In particular, X goes to X plus A. It is a special case for A equal unit matrix. And this is called translation, you know. The other special case is X goes to X, AX with some general A, but not small a. This is called linear transformation. So this affine transformation combines these two things, that linear transformation combined with addition. And that's why it is parameterized by these two guys, capital A and small a. This is a matrix which produces this linear part of this transformation, and this is a column which produces the translation. Now we can try to repeat it once more with some other pair. So first, by some BB, we obtain BX plus B. And then, with a pair AA, we obtain A applied to all that, plus small a, but just multiplying, we see that it is AB applied in X plus capital A acting on small b plus small a. And this can be called CX plus C. So what we learned, that if you do two affine transformations, one after another, first with B and then with A, you get once again an affine transformation with some C and capital C and small c. And of course, this is the capital C and this is the small c. So there is a rule how to combine or compose. We just compose two affine transformations, and we discover that it is affine transformation once again. So we have a new group. Our new group has an element, these pairs, and this is the way how they are multiplied. That if you have AA combined with BB, the result is AB, comma, AB plus A. This is the definition how affine transformations are combined, but the definition comes from the computation. This is very interesting group, actually, and it has some important subgroups. Notice that, for example, if both A and B will be orthogonal matrices, not general, but orthogonal, then this is just multiplication of orthogonal matrices, so C is also orthogonal because orthogonal matrices give us a group, so it is orthogonal. So you have a subgroup of this affine group with not general linear matrices, but just orthogonal matrices, or also SLN or any subgroup, but especially orthogonal is very interesting. And this is called Euclidean group then. So if A is from, say, SON, then these pairs comprise so-called Euclidean group. And Euclidean group is extremely important in both mathematics and physics because what are the operations of Euclidean group? Say in E3, in this room, translations and SO3 are rotations. So translations and rotations are very important transformations. Actually, we will see why when we will study Killing equations. It will be in several weeks. We come to the result that if you compute something about Euclidean space, you will discover these Euclidean transformations or Euclidean group as a group of isometries of Euclidean space. So this group is group of isometries, which will be explained, of course, what is it, of standard space, but including also this Rn. And so Euclidean group is extremely important for Euclidean spaces. And because Euclidean spaces are very important, so also Euclidean group is very important. And another interesting subgroup is when it is not On, but this more complicated version. Where is it? Not here, here, this OPQ. And especially when you have O1, say 3, but also for theoretical physics also O1n. So if A is from this group, because it is also group, the same holds that if A is from SO13, B is from SO13, so also C is from SO13. So it is again a subgroup, but it is not only subgroup of SO13 matrices, but plus these translations, do not forget, which are in this case 4-dimensional. Yes, because this acts on 4-dimensional columns. So we have something like x1, x2, x3, x4 goes to this matrix here on this x1, x4 plus some a1, a4. And this turns out very interesting in special relativity theory, that this part is Minkowski. This is called Minkowski space and usually called 0, 1, 2, 3, 4. We will see a little bit. And there is a linear part which is called Lorentz transformation, and there is this additional part which altogether now has a special name. So this name is Lorentz, and altogether is Poincare. So Poincare group is from this side is a group of pairs where this is from SO13 in acts like Lorentz transformations in physics. I do not explain it now, but we will see a little bit of that. Plus translations, it is already called Poincare group. So Poincare group is extremely important group in theoretical physics. Also this Lorentz group, but also the bigger group Poincare, which includes translations. So now I only wanted to say that we are speaking now about groups which are extremely important in theoretical physics. first of all, rotations in space, translation in space, then Lorentz transformations, Poincare transformations. So all of them are important in various parts of physics. And that's why, of course, we need to understand them as much as possible. And we will learn a lot about them. Now, because they are so important, it is a pity that they are not matrix groups. They are given by pairs. Here is matrix, here is also matrix, 1 cross n, but there are two matrices. And if, as I told you, when we want to compute Lie algebras and those guys, it is quite nice if these objects are just matrix group, given by one matrix. So we will be quite happy that we discover that these pairs of matrices can be worked with as with one matrix. And there, this trick is extremely simple and extremely useful. Namely, this matrix is like that. It is n by n. This is a column, so it can be put here. Then it is n plus 1 times n. So add here 0 and add here number 1. So do this trick. And now imagine that you have two matrices like that. The same with B. So we have now two matrices which are n plus 1 times n plus 1. One dimension bigger than the original A. Here is plus 1, here is plus 1. Now, where from is this matrix, or both? It is from GL n plus 1 R. Is it clear? The question is it trivial statement or not completely trivial, and we should check something? So I think that the part that it is n plus 1 is trivial, yes? But is it something a little bit not completely trivial? Yes. It is not clear at the very beginning that it is invertible matrix now. Yes. So the check is try to, well, first of all, try to compute the determinant of this matrix. So this is matrix of this structure, some A, B, C, 0. In general, what is determinant of matrix of this structure? It is a knowledge from linear algebra.
Because we just have to take a product of the
Yes, so if you have matrix, it is not diagonal because here is C, yes, but in spite of the fact that it is not diagonal, in linear algebra you can prove that something like this holds independently of C. So this 0 here is important, and the same holds if here would be 0 and here C. Yes. So this is a fact from linear algebra. I will not prove it. Yes, have a look if you do not know it. Now we have a matrix of this type here. Here is the 0 sector. So the determinant of this big matrix is determinant of this block times determinant of this block. This block has determinant 1 because it is just matrix 1 by 1. And this is by assumption not 0. Yes, so the determinant of this matrix is non-zero, so it is invertible. That's why I can use this notation. And now, if you do the multiplication, the second important knowledge from linear algebra, if you have block matrix, and each matrix can be artificially, each matrix can be divided to blocks in various ways. But if you do it and you multiply matrices which are divided to blocks, you can divide it by blocks as numbers. So for example, here we can do it as if we have just 4 elements in this matrix. So here we will have AB plus this A cross 0, which is 0. So nothing more. And here will be what? A on this B plus this A in and 1, it is plus A. Here, this block comes here, and it is 0. And these ones give you 1. So what we see, unfortunately, it is already not here, this result, that this is exactly our C and small c from this multiplication of this abstract group. Maybe you do remember, or you have it in your copybook, that what we obtained is just this what was here, that AB cross SX plus this AB plus small a. There was some computation before. So what we see, that we can reconstruct this type of multiplication by pure matrices, by not pairs of matrices. So when we include this, I mean now, this is called embedding, but exactly what is embedding is not so trivial, so we will see it in manifold theory, not too much, but just some beginnings. And actually this is really embedding in the sense of manifold. So we embed this pair to a bigger matrix, and now the gain is that now you can compute with this type of matrices, and effectively you compute with affine transformations. And if you want to also to use this action on this axis, you can check that it is done by this trick, that you compose n plus 1 dimensional column. This interesting part is x, and just some 1 added here, like here and here, this 1 and 0. And what you obtain is ax plus small a and 1 again. So everything which you do with these pairs, these affine transformations, including action on x and including multiplication or composition of these maps, you can do with matrices, with bigger matrix. This trick is used in physics, and what I was surprised that it is also used in elementary mathematics, which is taught here on computer graphics, because my son studied computer graphics, and so I opened the books of computer graphics. I found this trick in the very first page of the book. So this is well-known trick in computer graphics. Why this is important? Because of course in computer graphics you have to compute reality, that how it is translated and rotated in some computer games, for example, and so on, and then to map it to your screen, to two-dimensional screen. So geometry like that is very much used there, and you must do it effectively, quickly, and so on. So this trick is well known for anybody who studies computer graphics, for example. I was surprised, but this is the reality. Because in physics it is well known, but I thought that all physicists know something which this computer graphics, why they should not, something like that, but they do, yes, because it is important for them. By this trick, we will compute, for example, Lie algebra of this group very easily. Otherwise, it will be not so completely trivial. Yes. So this trick is really useful. Well, And the last line here is called direct product of groups. So I will explain it in two ways or two approaches. First is, let's have two general groups and now construct pairs. So this is an element of Cartesian product. The first element is from the first group, the second from the second. Now imagine that we have another such pair, some H or G1 tilde, G2 tilde. Now there is a question whether we can invent some way of group multiplication. So whether we can construct group which has these elements. Now we have already the set, but we need to find a way how they are multiplied, and multiplied in this way that it satisfies the axioms of group. And there is one very simple way that we can multiply already these two guys. So let's do it. And we can also multiply these two guys because they are from the group, from the second group. Let's try this as a definition and check that it works. That means that check that this prescription satisfies axioms of group. It is very easy, so I will not do it. Check yourself. And the result is that very simple proof, so-called, shows you that you just produce the third group if you have two groups. But we see that in a sense it is trivial, that nothing more happens here in this bigger group like happened yet in this original G1 and G2 separately. Because there is a separate slot for the first group, separate slot for the second, and there is, so to speak, no interaction between these two. There is also a more advanced construction, which is called semi-direct product, which needs some more information. This can be done whenever you have G1 and G2. If you want to do some more complicated but interesting construction, you need action of one group on other group on some specific properties. It is described in chapter, I think, maybe 13 or somewhere. You can have a look in the book. So this more complicated version is important, but this is a little bit more important, so to speak. So I will not treat this more complicated way of doing a third group for two groups, just this simplest one, because it doesn't need any structure more than just these two groups. Yes, the more complicated needs this action on one group, on another group, and so on. Now, how this can be done? So this is the end of the definition plus check in the abstract way. That abstract way is make an element, make this set, so pairs of these groups, the first element from the first group, second from the second, and do multiplication like that. But now, if you have matrix groups, like we usually will do, so it can be done in a slightly different way, that this pair can be somehow represented as such matrix. So this makes no sense in general, or well, it is a matrix with elements of groups elements. It is not very interesting, but in matrix groups, this is a matrix, yes, and this is also a matrix. And zero matrices are also matrices. So this is nothing more than some block-type matrix. And what is interesting, it is quite similar story like this affine group, that if you do this trick that a pair of two matrices you input somehow to the bigger matrix. Of course, if this is, it is n1 times n1, and this is n2 times n2, so n-dimensional, n1 dimensional and n2 dimensional square matrices, then it is n1 plus n2 and n1 plus n2 square matrix. Here is square matrix, again square matrix, and this is non-square matrix, this zero. But if you multiply such matrices like normal matrices from GL n plus n1 plus n2,
Please.
1, 2. Because of this knowledge that matrices can be multiplied by blocks, if we do this here, G2 tilde, we get this result by matrix multiplication, nothing more. Yes, matrix in the sense of these big matrices. So we reproduce this way, because if this is the rule how to combine or how to express this pair in terms of matrix, then it can be done also vice versa, that this matrix is to be represented by this pair. So the multiplication in terms of such matrices gives the same result as multiplication given abstractly some time ago. So this is a very useful way how to do this direct product of groups if the groups are given like matrix groups. Then just put them on diagonal, so to speak, to a bigger matrix. From this will be absolutely clear what will be Lie algebra. We do not know it, but if you have these two groups, this has its own Lie algebra, this has its own Lie algebra, we will see, and this new group also has to have Lie algebra, because we will see that each Lie group has its Lie algebra, and because the construction is like that, the computation of the Lie algebra of the composite group in terms of Lie algebras of the beginning groups is very, very trivial. If we work just with this representation, it will be not so clear maybe. And now also interesting point of view is that you can do it in opposite direction. That here it was in the direction that give me two groups and I will give you the third one. Yes. But there is also a point of view that give me just one group and I will prove that this group is actually G1. It is written like that also in multiplication of groups. This is either Cartesian product, it is without the definition of composition, or it is already at the level of groups, and then it is called direct product of groups in the same notation. So now the statement is that sometimes you are given a group, just one, and after some computation, you can prove that it is G1 cross G2 of some two smaller groups. And this makes sense to discover this because this means that study of this group can be reduced to study of that and that. That if you know everything about G1 and G2, actually you know everything about G because it is this trivial construction, yes? And of course, if this is product of two groups, these two groups are simpler than the bigger group, this G. So study of two simpler groups is equivalent to study of one group which we do not know, didn't know that it is so simple, only after some computation. So for example, one example on this, there is some theory about that, how you can, what proper, these two groups should be subgroups. Okay, I will have a look in general, that if you have this product, now product as groups, then you have a subgroup which is G1, say, tilde. It will be grouped of elements G1 and E2. E2 is unit element of the second group. Yes, the E is in general in group theory usually unit element, E, but there are now two unit elements, element of these groups and unit element of this group. So you can study these pairs, and also E1, G2 for any G2 and any G1 from G1 from G1, G2 from G2. Now, if you do the standard multiplication, that let's have one element of this type, another element of this type. What happens by multiplication? The left guys are multiplied and the right guys are multiplied, but the right guys are two times the same. Here is E2 and something. So E2 times E2 is once again E2 because it is unit element. So what we see that multiplication of these pairs is more or less the same thing like multiplication of these left slot elements, yes? That here's nothing happens. Here's nothing happens, and only these terms are multiplied. And how they are multiplied? As in G1. So that's why this group, G1, by this construction it easily seen, is isomorphic to this G1 itself, the first G1, yes? So this G1 is isomorphic to the G1 which was in the very beginning. And in the same way, this G2 is isomorphic to original G2. So this is the isomorphism, that this should be like G1. So this is some artificial adding of E2, yes, to G1. And why it is done? Because we want element of this product already. This element is already here. So whenever you have direct product, you have two subgroups inside the group. One of them is isomorphic to G1 and the second one is isomorphic to G2, whenever you have. Now, imagine you have some G. So in order to discover that this is isomorphic, once again, to some sub G1 and G2, this G1 and G2 has to be a subgroup of this group. And first subgroup and second subgroup. And it also has to have some properties. Not any two subgroups work in this way. So there is such small theory about these properties of these subgroups. I will not go to this theory, it is not needed. But I will show you one example which is quite important and quite simple at the same time. And it is that GL and R, the biggest one of all matrix groups, is SL and R cross GL1R, which is, what is GL1R? Can you describe me this group? What are elements and what is the multiplication in GL1R? Real numbers, and there are two groups with real numbers. One is addition group, and one is multiplicative group. So which one? Multiplicative and all real numbers. Which one? Which are forbidden? All non-zero, because this is non-zero determinant, and non-zero determinant for 1 by 1 matrices is non-zero element. It's because determinant is just this number. So it is also called sometimes R0 and plus, or various way how to notate this group. That's why I write GL1R, it is then clear what I mean. But also I try to explain that it is not complicated group, it is extremely simple group. Non-zero real numbers and multiplication. So what is the statement? You have arbitrary A from here. And the statement is that you can assign to this A some B from here and some lambda from here, such that if you have two matrices, E1, E2, of course of this type from GL and R, and you do the same with the first and the second, so then you can have two pairs, B1 lambda 1 and B2 lambda 2. And what holds is that if you do product of these original two A's from GL and R, you can instead do the product of these two elements, but by definition, it is then the element B1, B2, lambda 1, lambda 2, because this is the way how direct product works. And you lose nothing. The full information about this group is in some magic pairs, one with determinant 1 and one number. This is the statement. So how to assign to a general linear group, how to assign to a general matrix from there another matrix with determinant 1 and some number in such a way that if you multiply matrices, you multiply these pairs in the sense of direct product. So the easy way to do it, that try to write this A as lambda times B. Lambda is a number, and now this is lambda multiple of matrix. Yes, so it is like that. It is not abstract, it is lambda multiple of a matrix. So it is lambda here, and so on, yes, as usual. And now compute determinant of that. What is the determinant of this lambda multiple of this matrix? Imagine that this lambda is here inside. It is not here, but inside in every matrix element. What is the relation of the new determinant of the new matrix and determinant of the old matrix? What important property has determinant of matrices? What happens if you multiply some line or some column of a matrix by some lambda? Just one, the first line. Here will be lambda, and here the old elements. What happens with the determinant? By lambda. And what about if you have two lines multiplied by lambda? Lambda squared. So altogether, lambda to the power of n for n by n matrices times determinant of B. Now we can choose this lambda in such a way that determinant B should be 1. Is it possible? Well, there is an equation for lambda. That lambda is square root of determinant. No, sorry, not square root, but nth root. So we already see how to make these pairs. This pair will be B and lambda. So not any lambda, but this lambda. So if you have a matrix A, you compute determinant, make nth root of this determinant, which is possible because the determinant is non-zero. Maybe it should be better to have, well, there is another subgroup, quite interesting, of GL and R, which I forgot to define. GR plus and R. What it could be? Yes, because in GR in general, determinant is non-zero, so we can try to define the group with determinant positive. Is it a subgroup? If two matrices have positive determinant, the product also has positive determinant? Yes. So there is no group GL minus, yes, because the unit matrix has positive determinant, for example. But GL plus is a nice subgroup, and we need plus here because of that. So our matrix has positive determinant, so compute it, make this root, call it lambda, and then the rest call B. Yes, in this sense, the rest. That given A and here this determinant, square root or root, gives you unique matrix B. So make a pair B lambda out of these two guys. And then multiply A1, AB, A1 and A2. What happens? A1 is lambda 1 B1 times lambda 2 B2. Now this is lambda multiple of a matrix, lambda 2 multiple of some other matrix. It is clear that the two lambdas can go in front, and 2b's multiplied. So what does it mean? That if you make this so-called decomposition, and the same for 2, the multiplication of original matrices is done in such a way that these two lambdas are multiplied separately and 2b's are multiplied separately. So actually it is just in the sense which we need. Yes? So we can find subgroups in this GL plus and R one subgroup is matrices with determinant 1, which are inside GL, of course. Here, matrices are positive, so matrices with determinant 1 are there, and they form a subgroup. We know already. And what the subgroup, the second subgroup looks like? That numbers are not subgroup of n by n matrices directly. So what should we take as a second subgroup, which we need in general here? So we need to rewrite somehow this thing in order that we have product of two matrices, not number by matrix, but equivalent to this. Do we have some idea that this matrix is already okay because it is matrix? So if I want to write actually this thing, but formally as matrices, some first matrix and second matrix, n by n, how can I do it? Yes, lambda times Unix. And here B, yes? And this lambda times Unix matrix has determinant non-zero. Yes, you can check. Non-zero determinant, namely 1 here and here. This carries actually the information about determinant, and this carries the rest of the information about matrix A. So we can somehow divide the information within A to two parts. Information about its determinant is just one number, and information about everything else. It is in everything else is in B, and determinant is hidden here. So we already see that this is true. So in order to study the whole group GL and R with this plus, instead you can study SL and R and just real numbers with respect to multiplication, which are simpler groups. Yes. And many situations like that happen, that many groups are actually, what does it mean, are actually, that are isomorphic by some construction like that. You can prove that your group is isomorphic to several copies, product of several copies, which are subgroups, they are inside, and that's why studying of this big group is actually studying of the subgroups, because they are put then together in a very, very easy way by direct product. Something like that also happens with this more complicated product, this semi-direct product, but there it is more complicated. Here it is very simple. Okay, so it seems to me that I finished the week number 2. So officially now the second week finished. So please, if you have some questions concerning the second, especially the second week, but you can also ask something from the point of view of first week about tensors, because now we are going for 1 week to study something completely different, as Monty Python used to say, and it is the basics of manifold. And why we study manifold? Just the idea is that we want to define what is a Lie group actually. And for definition, we already have examples on it, we will see then. But in order to see that these are Lie groups, we first have to have the definition, what is a Lie group? And the definition needs the concept of manifold. And if you don't know what is a manifold, then the definition of Lie group is very complicated, because the definition of manifold is rather complicated. Yes, so the complicated things from definition of manifold then come to the definition of Lie group, if you don't know what is a manifold. If you know what is a manifold, the definition of Lie group is very short and very clear. Yes, that's why I prefer this way, that although we still will work in linear algebra sometime, we just we spend 1 week on manifolds a little bit, which is completely new idea. It is not linear algebra. Then we, at the end of the week, we define what is a Lie group, and then we go to Lie algebras a little bit and so on. So once again to linear algebra. Yes? And only on the second half, so to speak, of this course, we really will study differential geometry on manifolds. Now we will not study differential geometry on manifolds, just the idea of a manifold itself will be this week. So the rest of this lecture, actually, nothing more. So please, are there some questions for what was said, these matrix groups and the tensors from the very first lecture? No questions? Okay, so maybe this is before you can ask also whenever you want. So what is the idea of a manifold for beginners? Because manifold actually is a rather complicated stuff. You can study it in great detail and spend a lot of time on it. And this is not the aim of this course, even not the aim of the book. The book is much bigger. There are several courses inside somehow, including the courses which are present here, that mathematical physics #2, and then gauge fields and connections and this symplectic manifolds and so on. But including the complete book, the explanation what is a manifold is very short, actually, or not very in detail, because it is not needed, in my opinion. That for practitioner of differential geometry at the level of theoretical physics, you don't need to know too much about manifold. Of course, in some hard places, sometimes in very hard places, you come to something which you don't know about manifolds, then you will study because you are already prepared from other things. So you can study some technical details more complicated about manifolds when it comes to this problem. But for the very beginning, there is a danger if you study too much about manifolds at the very beginning. It is nice, but then you have no time to study why it is actually useful for you. That manifolds are useful to do analysis, differential geometry on it. And you have no time for this differential geometry, interesting and practical, if you spend too much time on the details of manifolds. It is done in several books in this way, and I think for physicists it is not very useful because they need to see why it is interesting. So I admit it at the very beginning that this will be much more about ideas, general the simplest ideas about what is manifold, which is, in my opinion, quite enough. If you have a look, for example, to one famous book, Mathematical Methods in, I don't know what, Classical Mechanics by Arnold, have a look what is the definition of a manifold. It is maybe 3 lines or something, if ever. It is something very short, because Arnold understood that at the level which he does there, it is not important. Somewhere in some appendixes, maybe some other facts are added, but on the first place when you meet manifolds, it is extremely, it is even much shorter than in my book. So what do we want manifold? In Slovak it is varieta. So what is the motivation? That when mathematical analysis is studied of functions of several variables. The question arises, where from is this argument? And probably the answer is that from Rn. So functions of one variables are these mappings, and functions of several variables are these mappings. Yes, so this function of several variables are this crank grinder that put here x1, here x2, here xn, or in like here, put this n tuple to the grinder, and here you will have a real number. Yes. But, for example, in theoretical mechanics, we had this pendulum. There is x, y is to the blackboard. And we know that the interesting thing about pendulum is just this phi angle. So, for example, Lagrangian is function of this. If mathematicians do not know what is Lagrangian, it is not important now at all. And pendulum, you perhaps know what is. Yes, so pendulum is some physical system, simple one to be studied, and it is done in theoretical mechanics by machinery of Lagrange function and so on. Now, the interesting thing is here is phi. But this, the question is this phi from something like that? Okay, phi is from perhaps R1 because it is function of one variable if you don't treat this phi dot nt. One variable phi. But phi is not from R really because there is some periodicity with this phi. That phi plus 2 pi is the same thing like phi plus nothing. And that means it is not actually from R1, it is from some part of R1. And there is some complicated thing that if this is R1, here is 0, then it is only some interval from 0 to 2 pi and complicated matters on the boundary of this interval. That this is here, this is not here, for example, or something like some periodicity and so on. So it is not that easy that you have really function of real on real axis, because the arguments behave strangely. So, and what is the object where we have this phi? It is a circle, this circle. And circle is not R1. There is a clear difference that R1 is from infinity to infinity, and circle is closed somehow that because of this periodicity. So we study, for example, Lagrangian mechanics on sets which are one-dimensional, but they are not R1. When we have not planar, the planar thing like that, but this spherical pendulum. Yes, we have some x, y, z, and you can go by the pendulum, which is like that once more. Also outside the plane of the blackboard. So the thing which here was so-called S1. It is one-dimensional sphere, which is a circle. Here, the configuration space is S2, which is called sphere, the usual sphere. Once again, it is two-dimensional because we need two coordinates there, for example, theta and phi, as we used. But it is not R2, because R2 is from infinity to infinity in two directions. And here is again some complicated way to say that from where to where are these angles, and some periodicity and so on. So clearly this is not a plane, it is something else, but it is two-dimensional. And what is important to notice that if you restrict to a very small piece of this sphere, a very small piece of this circle, so you cannot distinguish actually whether you are on the sphere or on this R space. And it is written in my book, and it was written in other books, that if you are short-sighted, I think in English term, that if your eyes are not perfect, if you only see for a very near distance, you need glasses, strong glasses, and you sit, for example, in the middle of the square, you do not see too far, you just see to the boundary of this square, and you do not know whether you are in R2 or on the sphere. Yes, you cannot say, because everything what you see is exactly like on R2. Also this is some short line, and short line, perhaps it goes like that. Then, yes, you cannot say. So again, it is not Rn in general, but if you sit somewhere and you do not see very far, you think that you are in Rn, or that it is possible that I am on Rn. I cannot distinguish. So this is the idea how the concept of a manifold emerges, that this is something which is very similar to Rn, but only on sufficiently small scale. And when you have a look globally, it may not be Rn. It can be Rn, but it also can be something different. Well, now the idea to grasp this, or to technical way how to grasp these ideas, is based on something like that, that this is our manifold which will be constructed, like this sphere, or many other things. The letter M is like here. And here is some part of this, small enough. Although the word small here is not completely appropriate, because you cannot measure how big is it. So it is not small in some very precise set. It is very intuitive. And you have a mapping to real Rn, which somehow helps us, this Rn, to have a look on this manifold. So this is a mapping, some phi, to phi of this O, which is inside Rn already. And it should be bijection. And it should be actually more than bijection, because officially this M should be topological space, which I don't want to explain what is it. There is a big theory about topological spaces, and we do not need it. But if you need it for your life, then open some book on topology and study. In my book, there is some definition, and it is not very much useful, in my opinion. So if it not be present in my book, you could be as educated as if it is there. So forget about topology and speak just about bijection here at this level. So you can go also backwards. And now what does mean? That you can go in both ways. That what is an element here? What is this guy? A point inside this phi O. We see that what is the space. So what is an element here? Yes, this is element of Rn. And what is it? It is a set of elements of R, yes, n real numbers. So if it is bijection, we can assign to this point n numbers from here. And also to all other points, we can assign n numbers, but this looks like coordinates. Usually, when we assign several numbers to points somewhere, we say that we introduce coordinates in this space. So this mapping is nothing more than introducing coordinates here. Yes, to this, it is called patch usually. And here we have coordinates because of this phi and phi to -1. Now we can take another patch, O primed, several. We officially at the very end, we have to have something which is called covering. Covering means that each point of this M sits in some O. Yes? So covering is here is O, here is O, and so on, many O's. Covering, it is also some precise thing that what is covering very easy, but just intuitive we need. And if we have two pieces of this covering, one O, another O, here should be also some phi primed. Again to Rn, but it is another copy of Rn. One copy serves for this phi, another copy serves for this phi primed. Yes, I will call this is the end. I will call this in this way, which is not completely standard. I want to say that my real numbers are called x1, xn here, and here it will be, for example, y's. y1 to yn. Yes, just to distinguish this copy of Rn and this copy of Rn. Okay, this is enough for this. Just think it over that there are also other things like Rn which have n coordinates, nothing more. So no questions to this? So thank you.